So in this chapter, we are going to talk about the structure of the atom and the periodic table. We are going to start by kind of putting on our history hats for a moment and look at how the different components of the atom were determined. It kind of began with Greek philosophers, right? And they believed there was this small particle, which they deemed atomos, which means uncuttable, that made up all of nature. And so there was a series of experiments in the 18th and 19th century that led to an organized atomic theory by John Dalton. And there's a rendering of him here in the early 1800s. And they're kind of like 6 big ideas. The first big idea was that all matter consisted of tiny particles called atoms. The second idea was that atoms cannot be created, destroyed, divided, or converted to any other type of atom. The third idea was that atoms of a particular element have identical properties. Atoms of different elements have different properties. Then atoms of different elements combine in simple whole number ratios to produce compounds. And then 6 was that chemical change involves joining, separating, or rearranging atoms. Now, when we look at this, this was done, like I said, in the early 1800s, and some of these have been adjusted because we have different discoveries. But postulates 1, 4, 5, and 6 still hold true today. So I want to talk about why postulate 2 doesn't hold true today, and it's because of radioactivity. Right, we can divide atoms. And then the reason postulate 3 doesn't still hold up today is because we discovered, right, isotopes. We're going to talk about isotopes in a second, but if you've heard about isotopes, it's basically the same type of atom, but with a different number of neutrons, right? So that means that those atoms don't have identical properties. So this is where we began, okay? And in like the late 1800s, a big discovery came on the scene, and that big discovery was electricity, right? And in that electricity kind of idea, with electricity, it opened the door for scientists to do different types of experiments. And so one of the types of experiments that one of the things they started experimenting with was a cathode ray tube. And basically, when you look at this, you run electricity through it, and there's an anode and a cathode, and there are particles that are attracted to the cathode and particles that are attracted to the anode. Okay, Eugene Goldstein was a German physicist. I don't have a picture of him that I could guarantee was actually him, so I wasn't confident with any of my sources. But he is sometimes credited with discovering the proton. This is still kind of a hotly contested area about who discovered it. But he was the first to discover that there were positively charged particles formed in the cathode ray tube, right? So he said, hey, look, in the cathode ray tube, there are positive particles. Right? And these were later kind of termed the proton. His work is really the first work that suggested there was a presence of a proton, but Ernest Rutherford described more about the proton, so a lot of times he's given credit for discovering it. But more recently, some people are looking at Eugene Goldstein's work to see and giving some credit to him. Okay, now that was in 1886. In 1897, J.J. Thomson, who is here, right, discovered the electron. Okay, and what his experiments did is they identified a negatively charged particle. So he's in the cathode ray tube as well, and he said, look, there's a negatively charged particle that's emitted from that cathode ray tube. Okay, and so what he did is, right, we have, if you can look up here, we have electricity that's being passed through this evacuated glass tube, okay? And the particles were deflected under the influence of electric or magnetic fields. And so what that means is if you were to hold a magnet up to this, and you know magnets have two poles, if the positive pole was held up, the beam of electrons would be attracted to it. And so that's what indicated that these electrons were negatively charged. And then, of course, if you flipped it over and there was the negative pole, then the beam of electrons would be pushed away. Okay, and that's what we're seeing there. So he was able to adjust electric and magnetic fields to balance out the deflections. And so because he was able to balance that, he was able to calculate the mass to charge ratio, which is a lot of times abbreviated as M over Z, so that ratio of the particle, right? And don't memorize this. I'm not going to ask you to repeat this number, but it's important to know. It's 1.76 times 10 to the 8. Coulombs is how we measure charge, and that's per gram. And so you can sometimes see that as a big C per gram. Okay. So he was able to do some calculations, and he was able to figure out the charge to mass ratio, which is one of the reasons he was really credited with discovering the electron. He just didn't say, hey, there was something negative hanging out there. He also went on and calculated this mass to charge ratio. Goldstein just said there are positive particles. And so, and did nothing else. And that's why there's some question about whether he should really get the credit for discovering a proton or not. But it's worth mentioning because to our knowledge, he's the first one who indicated there was something that was positive there. Now, so we have this mass to charge ratio. Scientists know that if you can figure out one of these, right, you can also figure out the other one, because that's how ratios are. If you can figure out one, you can figure out the other. And so they started to do experiments to figure out either the charge or the mass. So there's a guy that came along, his name was Robert Millikan, and he really advanced Thomson's work by figuring out the charge on the electron through his oil drop experiments, okay? And so he figured out the charge was 1.602 times 10 to the negative 19th. And so because we had that mass to charge ratio, now we can figure out the mass of an electron. And so there's our mass of an electron. How this worked is he would have oil drops here. And that was created using an atomizer. And it fell through a pinhole in this upper kind of chamber, and it fell through to the lower chamber. And as it was falling through in this lower chamber, he would shoot X-rays at it, and they would ionize the gas molecules and remove an electron, and that would be picked up in the oil droplets. And so he could adjust the electric field between the two charged plates here. And that's how he calculated the mass to charge ratio of the droplets. He looked at just thousands and thousands of oil droplets. And here is his original apparatus that he did this with. So that's kind of a cartoon description. There's the actual instrument. And then there is Robert Millikan. So we now know there's an electron. It's negative. We know its charge. We know its mass, right? And so there continued to be other experiments on the electron and different models of the atom. And one of the big models of the atom at this time, if it broke up, I advanced too far. So I apologize for that, but you didn't miss anything. Okay, so J.J. Thomson came along and, he discovered those electrons using a cathode ray tube, but he wasn't really sure where the electron fit into the structure of the atom. So he proposed a plum pudding model of the atom, which said, hey, look, electrons are distributed throughout a positively charged sphere. Okay, so he said, look, we know there's something positive that's hanging out here. Goldstein is the one that said that. Then he knew that there were electrons running around, and these two things were contained within the atom. And so he said, look, it's like the dessert plum pudding, which is an English dessert that we don't see very often here. This would be similar to like bread pudding. If you're from Louisiana. So I put a picture here so you could see what plum pudding is. But basically you have a uniform cake, and then you've got these dense areas of plums. You might even think of this maybe as the chocolate chip cookie model. But basically, what he said is, look, we got positive charge here. It's very, very diffuse. It's distributed all across here. And we have these little electrons that are embedded in this positive charge, like plums in plum pudding or chocolate chips in a chocolate chip cookie. Okay, and so that was the model of the atom that he proposed. Now, the plum pudding model just didn't really last long because radioactivity was discovered, kind of figured out. So Henri Becquerel was a French physicist, and he really was investigating radiation that was emitted from pitchblende, which is a uranium ore. And so this is pitchblende, right? And he surmised that some materials produce invisible radiation consisting of charged particles. Okay. And it was pretty commonly thought that the radiation was similar to the X-rays used by Thomson. But Becquerel and the Curies, so Marie and Pierre Curie, determined that that radiation was actually charged particles. So they also showed that radiation consisted of small particles. And so when we talk about this and we talk about radioactivity, there were different radioactive particles that were used to investigate different areas of the atoms. And so it's helpful here to define radioactivity. It's the spontaneous emission of high energy radiation and particles. And the two particle types that we're gonna look at here, and we'll look at more later in the course, are beta particles. These are very high energy electrons. And alpha particles. Right? And these a lot of times are shown as a Greek letter alpha. These are shown as the Greek letter beta. They have a +2 charge. All right. And the mass is the same as a helium nucleus. Okay. So radiation was discovered, right? And this led a physicist from New Zealand to attempt to validate the plum pudding model. And so what he did was, and his name was Ernest Rutherford, and he designed what's now called the gold foil experiment. So he had a radioactive source. It emitted those alpha particles that we talked about. And so the alpha particles travel along and they hit a thin gold foil. And the trajectory of the particles could be determined by observing fluorescent images created by the collision of particles with the fluorescent screen around the target. So they had this big fluorescent screen around the target, and when the alpha particles would hit the fluorescent screen, they would light up. And so they could tell where these alpha particles were landing. What they expected to happen, right, is if the positive charge was very diffuse all the way through here, they would expect that these alpha particles would pass straight through because the alpha particles are charged, right? So if the plum pudding model was correct. Rutherford expected most of the positively charged alpha particles to pass straight through. Right? They might be deflected a little bit, right? Because they might, kind of be repelled a little bit or attracted a little bit. They're positive, so attracted a little bit to that negative charged electron that's embedded there. But they mostly expected them to shoot through, okay? He was shocked when he got big deflections, right? So it was nothing like he experienced. What they started seeing was some would be deflected with wide angles, a lot would pass through, and some would even bounce back at the alpha emitter. And so this is actually kind of what they saw was that bouncing back. And so what he proposed, right, was that there was a dense, so what he proposed is that there was a dense region of positive charge, right? And that's why his alpha particles, which were positively charged, would come in, hit it, and bounce back. And that's called the nucleus. And so when you read his firsthand account of this, it's really interesting. You're so surprised. He said it was like shooting a shotgun at a piece of tissue paper and the bullet bouncing directly back at you, right? So that's how big this experiment was. And so it changed the model into a nuclear model. Rutherford and others continued to perform different reactions where they bombarded atoms of one element with alpha particles and converted it into another element. That's transmutation. And many times these reactions produced positively charged particles, which had the same mass as the hydrogen atom. And Rutherford called those particles protons. And so that's kind of where we get that term. Now, the other thing that we see in the nucleus of the atom is the neutron, okay? And James Chadwick, an English physicist, is the one that's kind of credited with discovering the neutron. And what he did is he took a polonium source with alpha particles and bombarded a thin sheet of beryllium, okay? And this was a really high energy radiation was emitted by the metal, and it was not deflected by either electric or magnetic fields. And so that indicated that it didn't have a positive or negative charge. And so Chadwick named these particles neutrons because they were electrically neutral particles, and they had a mass that was slightly greater than that of protons. So those are the three kind of parts of the nuclear atom. So just to review what we kind of walked through history to look at is we have an atom, right? And it has a nucleus. This is the nuclear atom model. And we've got a positively charged center, which contains nearly all the atom's mass. So we have a nucleus. It's a positively charged center that contains nearly all the atom's mass, okay? There are two types of particle in the nucleus. There are protons, and these are positively charged. And there are neutrons, and these are neutral. So neither positive nor negative. And then we also have electrons. These are outside the nucleus. Right? And they are negatively charged. Okay. This is a comparison for the size of a nucleus with that of the atom. So the nucleus is very, very small, and then electrons can be found somewhere in this very, very large region. A really good analogy is if you were at the Titans Stadium and the football was the nucleus, this area here would be the rest of the stadium, right? If we were looking at that scale to size. So in this screencast, we have looked at the history of discovering the proton, the electron, and the neutron. And we've also looked at the nuclear model of the atom.